Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who recognized and selected CSI Training as the world leader for quality instructional products. The next 40 minutes will reveal the keys to successful alignment. Whether your alignment system is mechanical, electromechanical, or laser, you will be able to apply the tips and techniques presented here to strengthen your abilities and confidence to perform precision alignment and enhance your reliability-based maintenance program. We will briefly consider the diagnosis of misalignment using spectral and waveform data, as well as the steps to detect and correct soft foot condition, piping strain, and coupling runout. Precise steps are shown to use reverse dial indicator, electromechanical, and laser systems to achieve a quality alignment and be within tolerances to increase the machine's life and decrease maintenance costs. Let's look at the characteristics of misalignment to see the effects on a machine and how they will show up in spectral and waveform data. When two shafts are aligned, their center lines will be a straight line from the end of one shaft through the end of the other. This common center line is called a common collinear axis. Misalignment, then, is any condition where the shaft center lines are not in a straight line during normal operating conditions. One common type of misalignment is angular misalignment. The two shaft center lines meet, but they meet at an angle. The shafts could be at an angle horizontally or vertically, but it's typically a combination of the two. The second type of misalignment is offset or parallel misalignment. The shafts are parallel, but the center lines of the shaft don't match up. In fact, the shaft center lines never cross as they do in angular misalignment. Although angular misalignment and offset misalignment are sometimes referred to as coupling misalignment, we are actually aligning the shaft center lines. When the machine is running in an angular misalignment condition, the two shafts are tied together with a coupling that forces the ends of the two shafts into better alignment. This pulls on the shafts and produces movement and distortion of the shaft as they attempt to align themselves. The shafts are forced in the axial direction once during each shaft revolution, and they move radially as they are pulled by the coupling. In spectral data, then, we expect to see a peak at the shaft turning speed in the axial direction. The radial directions, both horizontally and vertically, will also have a peak at shaft turning speed. With offset misalignment, the shaft tends to move or bump a sensor 2 times during each shaft revolution in the radial directions. However, there is very little movement in the axial direction. In the real world, though, there is usually a combination of angular and offset misalignment combining the responses. Both angular misalignment and offset misalignment produce repetitive vibration, which will be indicated in the waveform data with a very repeatable pattern. In these examples, we have looked at angular and offset misalignment in their purest sense, without regard to the effects of various coupling types, machine characteristics, and so on. In reality, various coupling types produce different responses in spectral and waveform data. In tests performed by CSI, a machine was aligned and misaligned with exact amounts of purely angular or purely offset misalignment and repeated for 5 coupling types. Each setting was run under load and vibration measurements were made. The results varied for the couplings. The 3-jaw coupling showed the most vibration at 3 times shaft turning speed, with multiples appearing in severe misalignment conditions. The bun or rubber tire type coupling and the rubber gear coupling had high 2 times shaft turning speed peaks in the radial direction. The shim pack coupling had peaks at both 2 and 6 times shaft turning speed. The grid type coupling had a high 4 times turning speed peak. Because the various couplings produce different responses, it is important to know the flexible coupling type for a more accurate diagnosis of the alignment condition. Sometimes we are asked, why worry about misalignment? Isn't all I need a good flexible coupling? John Piotrowski answers this in his book, Shaft Alignment Handbook, where he points out that coupling manufacturers will often quote information on allowable misalignment for the coupling and not the equipment to which it is coupled. These tolerances seem to lull the user into a sense of complacency, leading one to believe that accurate shaft alignment is not necessary because the coupling can take care of any misalignment. Although the coupling may be able to handle these stresses, the mechanical seals, bearings, wear rings, and so forth cannot. The stress created by the misalignment is still passed on to these components, causing premature failure. So it is necessary to be concerned with misalignment. In contrast, a machine in good alignment condition extends the life of the bearings, mechanical seals, the couplings, wear rings, and the shafts, as well as reducing vibration and minimizing shaft bending and cyclic fatigue. Quality alignment is proactive and removes the root cause of failures due to the forces of misalignment. In fact, studies have shown that machines properly aligned can reduce electrical power consumption by at least 4 to 9%. Misaligned conditions can be detected using at least 5 predictive maintenance methods that do not require an interruption of the process. They are spectral and waveform analysis of vibration data, as was shown earlier, phase analysis of vibration data. Another is to measure coupling and shaft temperatures using an infrared temperature probe or infrared thermography. And the strobe light can be used to actually see shaft, coupling, or machinery movement in slow motion. Because phase is the relationship between 2 points, it can be used to determine how a machine moves compared to a marked point on the shaft. Mark the shaft with reflective tape for the shaft reference, and use an infrared phototac to pick up a signal each time the shaft turns. This is the constant, while the vibration sensor is our variable, that is, it will be moved from one position to another, and the relationship between the phototac and the peak of vibration can be measured. Monitor the horizontal bearing location on one side of the coupling and read the phase angle. When this phase reading is compared to the one across the coupling, we can determine how the machine is moving. If the phase readings are about the same, then both sides of the coupling are moving together or in phase. However, when there is approximately a 180-degree difference in the phase readings, one component of the machine is moving one direction, while the other component is moving the opposite direction or out of phase. This is characteristic of misalignment conditions when the 3-jaw coupling, the shim-pack coupling, or the bun-type coupling is used. The grid coupling and the internal gear coupling typically don't follow this pattern. Peak and phase readings made in the axial direction across the coupling can also be used to detect a misalignment condition. Readings approximately 180 degrees apart mean the machines are moving opposite each other and indicate angular misalignment. All of these rules of thumb are based on the sensor being turned the same direction for comparative measurements. The readings will change 180 degrees when the sensor is turned around. The forces of misalignment cause flexing and movement of the shaft and coupling and generate heat. This heat can be measured while the machine is running to determine the presence of misalignment. In another video program, Introduction to Infrared Thermography, we showed examples of thermographic images from tests with various couplings and misaligned conditions. Some of the coupling temperatures from an aligned condition to a misaligned condition increase by as much as 65 degrees Fahrenheit. The movement of the coupling due to a misaligned condition can sometimes be seen in slow motion when a strobe light is flashed close to the rate of the shaft turning speed. All of these methods can be used to detect misalignment, but other symptoms of misalignment are apparent without the aid of tools or instruments. Some of these symptoms are excessive oil leakage, powdered rubber under couplings that use rubber inserts, leaking seals on pumps, soft foot condition, broken foot bolts, oil shimmering under the machine foot or base plate, and premature failure of bearings, seals, shafts, and couplings. The benefits of precision alignment far outweigh the costs, and the price of poor alignment is much higher in the long run than it first seems. There are many methods for proper shaft alignment, and they're illustrated in the next section. If you were to hire a contractor to align a machine, would you get better alignment from a dial indicator set that costs a few $100s, or a laser set that costs tens of thousands of dollars? The key to remember is, tools do not align machines, people do. The tools are merely used to measure the alignment condition, and some tools help calculate the machine moves, but the better tools help a competent person to perform the same job faster and with less risk of error. Some tools and alignment methods were never intended as the final alignment, but in industry they've often been used as the final fix. Two brothers, Bo and Boo, illustrate this well.
Bo, how do you do alignment on pumps and motors?
Use the old eyeball and shim it.
That's all. Is there any other way?
When I want to get it close, I use a straight edge and a flashlight.
The straight edge and flashlight method was only intended for a rough alignment during installation and is the least accurate method of alignment. The straight edge is used for the offset misalignment and a taper wedge or feeler gauge for the angular position of the shaft. However, it can only work on certain couplings, and because it does not require special tools, it is often used as the only alignment step before returning a machine to service. When only one shaft can be rotated, the face rim method can be employed, which uses a dial indicator on the coupling face to measure angular misalignment, and a dial indicator on the rim to measure the offset misalignment. The dial indicator readings are then graphically or mathematically projected to the machine feet to determine the required adjustment and shimming for each foot. A dial indicator has a spring-loaded plunger in the back, which turns the needle in the face as it is moved in or out. The dial indicator is positioned near a part of the machine so that the pin is pushed about halfway in. The face of the dial rotates, so this position can be marked as 0. As the shaft is turned, the tip writing on it changes the dial reading with any change in the relative position of the shaft. When the plunger is pushed further in, the needle moves in the positive direction. When the plunger moves farther out from the dial, the needle moves in a negative direction. Most dial indicators are designed to measure in mils. 1 mil equals 1/1000th of an inch. The face rim method works well for short spans, and it is easier to visualize the readings. The disadvantages are that it easily becomes a trial and error process. Any axial shaft float will induce error in the face reading and affect the angular misalignment calculations, since this face reading is used to determine the amount of angular misalignment. When using the face rim method, it is critical that the coupling is true. Often couplings may be bored off-center or at an angle, which then causes the outer rim and face to be eccentric or have runout. Since the corrections for misalignment are based on these surface measurements, only a trued coupling will produce adequate results. The reverse dial indicator method is used when both shafts can be rotated together. A dial indicator is mounted on each shaft, and the dial is actually measuring across the coupling to record the relative movement of the opposite shaft. These measurements are then mathematically or graphically projected to the machinery feet, where corrections are then calculated for adjustments and shimming the feet. This method can be used for longer spans than the face rim method, and because the shafts turn together, it is independent of coupling runout. Axial movement does not affect the measurements, because the dial indicators do not measure in the axial direction. However, if the coupling has any torsional shift as the shaft is rotated, then error will be induced into the reading, and the bar holding the dial will have some amount of sag that needs to be compensated for. The reverse dial indicator method can be simplified with electronics, such as this CSI Model 8110, which uses a patented method to automatically compensate for bar or bracket sag. The principal difference between the reverse dial indicator method and the electromechanical system is the dials are replaced with digital heads that make the readings and transfer the data into an alignment analyzer, which calculates the machine moves and required shims under each foot. Although the electromechanical system is more costly, the calculated moves reduce time and minimize the error factor, saving manpower and downtime dollars. Bar sag or bracket sag is not a problem with a two-head or dual beam laser system, which emulate the reverse dial method and mounts laser beam heads in place of the dial indicators. Each head sends a laser beam and receives one from the opposite head. The change in position of the beam on the receiver is tracked as the shaft rotates, and the information is then sent to a receiver on the alignment analyzer. This wireless system is the most precise of all the systems. Because there is no bracket sag, it is unaffected by coupling runout and any axial float in the machine. The laser system can be used over longer spans than the reverse dial method, but its accuracy can be affected by airborne particles. When an alignment analyzer is not available, the machine moves must be determined by graph or mathematical equation. Whatever method you use, there are common steps that must be completed before actually performing the alignment procedures. These are explained in the next section. The alignment process involves 7 steps that must be performed to ensure personnel safety and successful alignment. First is the pre-shutdown preparation that facilitates a faster, thorough job. Then shut the machine down. And the third step is a series of pre-alignment checks. Then the misalignment measurements can be made. Next, reposition the machine and repeat the measurements. Repeat these steps until the misalignment is well within tolerances. Restart the machine, and after the unit has returned to operating conditions, recheck the data used to calculate offline to online conditions. Before shutting down the machine, take the time to perform these 4 steps, and you will decrease the time for the actual alignment. First, obtain all the tools and measurement devices. Include the alignment fixtures and mounting tools, whether mechanical, electromechanical, or laser. Get the dial or digital indicators, magnetic stands, a good 1-inch outside micrometer with at least a 1 mil resolution, feeler gauges 3.5-inch and 6-inch long, measuring tape, pre-cut stainless steel shims of appropriate size, brass or stainless steel shim stock, tin snips, small hammer, needle nose pliers, a plumb bob, an extension mirror, chain or strap wrenches, automatic center punch, and a permanent marker. Be sure to include the tools needed to remove the coupling guard, loosen the feet, and move the machine, including wrenches, jack bolts, and hydraulic jacks. Remember to include the vibration analyzer for before and after data, and a device to measure the machine temperature, whether it is an infrared thermography system or a temperature sensor. Collect vibration data and other operating data. Be sure to collect the necessary data to determine the online to offline running condition. Inspect the base plate, foundation, grout, and hold downs. Notify operations and follow all safety procedures to shut down and lock out the machine. The online temperature data will be used later to help you determine thermal growth. Thermal growth is the change in the physical size of the machine from the offline condition to the online condition. If thermal growth is not taken into consideration during the alignment process, the smooth running condition and restart may become a rough, vibrating machine when it returns to its normal operating temperatures. Most machinery operates well above ambient temperatures, and the actual size of the machine will increase as the temperature increases. This would not be a problem if the machine grew the same throughout, but that is seldom the case. Instead, the fan end of the motor will typically be cooler than the coupling end and therefore not grow as much. If the driven unit is a pump and it is transferring a hot solution, it could grow more than the motor, increasing the misalignment. On the other hand, if the pump is pumping a cold solution, it will actually shrink smaller than it is at ambient temperature. This thermal growth will affect your alignment results and, if neglected, could lead to machinery failure. There are several tools and methods to measure thermal growth, such as Essinger bars and Dodd bars, that are used for measurements at both running and ambient conditions. One technique to estimate vertical growth does not use special tools except a temperature probe. The temperature is recorded in at least 4 positions in a line from the foot to the center line of the shaft, and is measured for each foot and bearing location on the machine. Temperatures are recorded for both the online and offline conditions, and their differences are averaged to a single number at each bearing location. The amount of expansion is then calculated using the formula E equals T times L times C, where E is the expansion in mils, T is the temperature in degrees Fahrenheit, L is the length of a vertical line from the center of the shaft to the shim plane, and C is the coefficient of thermal expansion in mils per inch degrees Fahrenheit. The coefficients differ from material to material as shown here. The coefficients all seem to be very small numbers, but notice that aluminum is twice that of cast iron. This means that if a motor housing is aluminum and is coupled to a cast iron pump, the motor could actually grow twice as much as the pump with the same temperature increase. The temperature measurements and calculations must be made at each bearing location. These numbers are the expected amount of growth in mils when the unit is returned to normal operating condition, and this growth must be compensated for when determining the amount to shim each foot. After the machine is shut off and locked out, there are 7 checks that must be made before any misalignment measurements can be performed. Some of these may require additional corrective work, but will assure successful alignment. Remove the coupling guard and inspect all accessible rotating parts. If the coupling has a rubber insert, check for rubber powder because this is an indicator of the amount of misalignment, and a worn rubber insert can allow too much looseness in the coupling, accelerating the wear and increasing the vibration. On lubricated couplings, check for leaking grease as an indicator of wear or looseness. Check the keyway for wear and a loose key as an indicator of a loose coupling. Check the coupling for tightness and any play between coupling hams, including movement in the axial direction. Loosen the foot bolts and clean the top and bottom of the machine feet and the base plate, checking for any burrs or rough surface. A heavy-duty cleaning agent will help loosen and remove any residue. Check the foundation for cracking and loose grout. If the base plate has several coats of paint or is rough, it should be machined to a smooth surface. Check the condition of any existing shims, cleaning them and inspecting for burrs or rough surfaces. Discard any distorted, rusty, or aluminum shims. Verify the thickness of shims over 25 mils thick with a good outside micrometer that has a resolution of at least 1 mil. The shim should be the same thickness throughout. Mark the thickness on the good ones and record the thickness that was under each foot. There should be no more than 5 shims under any foot at the same time, because the stiffness of the foot decreases as the number of shims increases. If several shims are to be used on a foot, sandwich the thinner shims between the thicker ones. Measure shaft runout for a bent shaft condition and measure the runout on the coupling. To set up for measuring the shaft and coupling runout, mount a dial indicator on the machine base or the machine component and place the plunger of the dial indicator on the shaft with it pointing to the shaft center line. Be sure the plunger is depressed about halfway to ensure good contact at all times. Zero the dial indicator and rotate the shaft, watching the dial indicator through its full swing. Repeat the procedure on each coupling hub. This technique can be used to determine whether the coupling was bored askew, whether it was bored off-center, or whether the shaft is bent. Any of these conditions require corrective work. If the coupling runout is greater than 5 mils, replace it. It is especially critical to have a true coupling when using the face rim alignment method. Soft foot is the condition where one or more feet are not on the same plane with the others. It can also be when feet do not rest flat or solidly along the surfaces. The actual machine feet could be true, but if the base is not true so that the feet do not sit squarely on the base, then the effect is the same and is still called a soft foot condition. When a soft foot is tightened down, it pulls on the machine and can warp or distort the machine casing, causing a bind on the rotor and preloading the bearings and seals, creating improper internal clearances and increased vibration. This soft foot condition decreases machinery life and causes even the most skilled craftsmen to chase their tail during the alignment process. Check all machine feet, correcting the soft foot, and the machine will run better, and you will have an easier job of aligning to tolerances. The soft foot may be one that is bent down, bent up, or parallel to the base, but not touching. The soft foot could even be due to an untrue base plate. To check for soft foot, make sure all the hold-down bolts on the feet are loose. This is where science becomes an art. Use a feeler gauge to measure the clearance under each foot, increasing the thickness until the feeler gauge fits firmly under the corner of the foot. Record this measurement for this corner of the foot and continue measuring each corner of the foot to determine the profile of the clearance. After the measurements have been recorded for each of the 4 corners of the foot, cut shim stock to fit the profile. Where one side is thicker, use 2 or more layers of various thicknesses of shim stock. Depending on the measured clearances, the shims may need to be square, C-shaped, L-shaped, a straight strip, or any combination to create a customized wedge. Remember to sandwich the thinner shims between the thicker ones. Using needle nose pliers, insert the shims under the foot and check the clearance again with a feeler gauge. If the clearance is 2 mils or less under the entire surface, then move to the next foot and repeat the process. This must be done for each foot to correct the soft foot condition. If the machine component to be aligned is a pump, compressor, or turbine, then check for piping strain. Piping strain is any condition when the pipe flanges do not freely make a perfect match, but must be forced into a perfect match by some means. This forced match distorts and weakens both the pipe and the pump. The pump casing is pulled, causing flexing which moves bearing locations, bending the shaft. So a pump motor combination can be in perfect alignment, but connecting ill-fitting piping can force it into a misaligned condition. To check for piping strain, make sure all feet are tightened to the correct torque. Then set up 2 dial indicators on the coupling end of the pump bearing, one in the horizontal position and one in the vertical position. These dial indicators should be mounted on the base so that they are independent of machine movement. This means the one for the vertical reading will probably be reading the bottom of the shaft due to the short length of the mounting brackets. To zero and check this dial, use a small mirror to read it. After the dial indicators are in place and set to 0, loosen the piping flange and read the dial indicators again. If the movement is more than 2 mils, correct the piping strain. Expansion joints can be used in the pipe length and are designed to absorb thermal growth and can withstand some small amounts of misalignment. However, they can only correct for so much misalignment and should not be used in extreme cases of pipe flange misalignment. In extreme cases, a customized pipe filler ring called a Dutchman may be installed. This ring should be custom made to correct for both angular and offset misalignment of the flange. There are arguments about which to perform first, the alignment or attach the piping. If piping strain corrections are made properly, it should not matter. One consideration that is often overlooked in the alignment process is bar sag. Anytime dial indicators are used for the alignment process, there will be some amount of deflection of the bar due to gravitational force. When the shaft is rotated, the bar sag varies and must be measured and accounted for in the alignment process, or all the calculations will be in error. To measure bar sag, extend the bar to the length it will be used during the alignment process and mount it onto a mandrel or straight section of pipe. It should be mounted exactly as it will be used on the machine, including the bolt torque. Be sure the pipe is of sufficient size and wall thickness that it does not sag itself. Position the dial indicator to the top and zero the dial. Rotate the shaft to the bottom and read the dial. It will be a negative number equal to twice the distance of the bar sag. There is sag while the bar is positioned at the top. However, we zeroed the dial indicator as if there was no sag. So the reading at the bottom is twice the actual bar sag. This amount must be compensated for when performing the actual alignment. When the bar is rotated to the 90-degree position or the 270-degree position, the dial should read half the bottom reading so that they sum to the bottom reading. Remember that this bar sag must be determined prior to the alignment job and must be compensated for in the vertical readings of the face rim method and the reverse dial methods. However, when CSI's Model 8110 alignment fixtures are used in conjunction with the UltraSpec 8000 alignment analyzer, a patented method is used for determining the total bracket sag after the brackets are mounted on the machine. Remember to perform all these pre-alignment checks before the actual alignment. First, inspect rotating parts for wear. Measure the shaft and coupling runout. Clean the machine feet and base plate. Check condition of shims. Check for soft foot. Check for piping strain and measure bar sag if applicable. Now, we are ready to perform the alignment. Earlier, we reviewed the alignment methods and noted the differences among the methods. Although they seemed very different, they all have the same 3 steps. First, measure the misalignment, and next, make calculations, and then adjust the machine. Even Bo and Boo performed the same steps.
Last time I had a job like this, it took me 2 Pepsi cans. Hey, Boo, give me 2 Pepsi.
I don't have 2 Pepsis, but I got a Pepsi and a Mountain Dew.
Although the same basic steps are required for each alignment method, the tools to measure and calculate the moves vary greatly. Tools for moving the machine vary nearly as much. It is the preciseness of the measuring, calculating, and moving that makes the difference in the alignment job. We will first look at the reverse dial indicator method, and then the electromechanical system, and finally the laser setup. All the alignment methods require accurate documentation so that the alignment could be set up again to save time. The documentation should include the name of the person performing the alignment, the results of the inspection, the soft foot corrections made, any piping strain and corrections, the amount of thermal growth, the orientation of the machine, that is, which is the left and right side, and the machine dimensions. Since the corrective moves are calculated for the foot locations, accurate dimensions must be recorded. Measurements must include the distance from the center of the hub to the dial location, from the dial location to the bolts on the inboard feet, and the distance between feet. These measurements should be accurate within 1/8 inch. For the reverse dial method, mount one indicator bracket on the shaft or coupling hub with its dial indicator resting on the opposite shaft or coupling hub. Be sure to mount it so the plunger is pushed in about halfway. The plunger must have some amount of pressure on it during a full 360-degree swing of the shaft. In severe misalignment, the plunger may either ride away from the shaft or bottom out. Either case will generate invalid data. The second dial indicator is mounted in the same way as the first. Rotate one to the top or 12 o'clock position and zero the dial. To check that readings will be accurate, rotate the shaft to the 3 o'clock position and record the dial reading, being sure to note whether it is positive or negative. Rotate the dial to the bottom and record its reading. Continue rotating the shaft to the 9 o'clock position and record the number. To check that the measurements are valid, a rule of thumb can be used that the 2 side readings should total to the bottom reading. If the bottom reading is minus 15 mils, the side readings could be any numbers that will sum to that, such as minus 8 and minus 7, or minus 17 and plus 2. If the data validity rule indicates bad data, then there is a mechanical problem or the plunger on the dial could have bottomed out. Piping strain, soft foot, and a loose coupling will cause the validity rule to be off. Correct the mechanical problems before continuing. If you are using the graphical method for calculating the moves, be sure to compensate for bar or bracket sag. Use the values determined for the bar sag and subtract them from the bottom or 6 o'clock reading. A good method to calculate the machine moves is the formula method. This method is based on selecting one machine as stationary and the other as movable. The formula for the move is 1/2 the quantity of M1 plus M2 times the leg over the spacing minus M1, where M1 is the reading at the stationary machine and M2 is the reading at the movable machine. The leg is the distance from the location of the stationary machine reading to the leg to be moved, and the spacing is the center-to-center distance of the dial indicator brackets. This formula calculates the move for one leg plane in one direction only. This means the formula must be used 4 times for the complete machine move. Draw the machine noting the measurements. Since we must solve for either the inboard legs or outboard legs separately, we will label their respective distances L1 and L2. Let's use 6 inches as the spacing in this example and solve for the vertical move for the inboard foot. First, normalize the readings by subtracting a number from both sides that will leave one of them 0. The vertical readings are already normalized because the top is 0, but remember to subtract the bar sag from the vertical reading. Now plug in the numbers to solve for the vertical move for L1. M1 is 27, M2 is 0, L1 is 24, and the spacing is 6. M1 again is 27. This gives us a number of 81 divided by 2, which is 40.5 mils. Since the number is positive, the leg must be moved up 40.5 mils. Repeat the steps, solving for the vertical move of the outboard feet and the horizontal moves at each set of feet. When moving the machine in a horizontal position, set up dial indicators at each foot that will be moved, being sure to set them to 0. As you push the machine with the jack bolts, watch the dial indicators and move the machine the calculated distance. If no jack screws are available, temporary jack bolts may be mounted on the nuts of hold-down bolts to move the machine horizontally. When the machine has moved the calculated amount, torque the hold-down bolts and take another set of readings. Repeat the steps until the machine is within tolerances. In the electromechanical system, the indicators are the digital indicators and are referred to as heads. These electronic heads transfer data measurements from the 4 90-degree positions to an alignment analyzer, which then calculates the moves for each foot. The brackets for attaching the heads must be mounted to the shaft or coupling and require a surface of at least 3/4 inches wide. The farther apart these heads are spaced, the more accurate the calculations will be. Mount and level one bracket, then mount the other bracket, being sure to level it also. It is best that the brackets are in the same plane. Then mount the heads on the brackets, positioning the stems and bars to ride on the plunger of the opposite digital indicator. The benefits of an electromechanical system are more than just time saving. It measures bar sag with the heads and bars installed, therefore eliminating that pre-alignment check. It reduces error from reading dials by digitally measuring the movement and transferring it to the alignment analyzer, which calculates the moves. If the machine is not coupled, position it axially before making any measurements. Distances between feet and from the feet to the face of the heads are required for accurate calculations. The most critical distance, though, is the distance between the faces of the heads. All these measurements need to be as accurate as possible, so it may be necessary to use a plumb bob to measure the distance from a foot to the face most accurately. The distance between the faces should be within 1/16 of an inch, and all other dimensions should be within 1/8 of an inch. Enter all of these dimensions into the analyzer. Be sure the feet are torqued to the required amount before making your readings. One benefit of the electromechanical system is that it doesn't require a full 360-degree swing in order to calculate the machine moves. At least 3 readings are required, so a minimum rotation is 180 degrees. The 4th value is then calculated from the data validity rule. Be sure the heads are in the on position and 0 them at the top or 12 o'clock position. Rotate the shaft slowly, stopping at the left, right, top, and bottom positions. In the analyzer, view the data and the recommended vertical moves. The vertical moves should be made first because it often affects the horizontal moves. The analyzer calculates 6 potential solutions that will correct the misalignment. Toggle through them and select the one that will be the simplest to perform. And if the machine is not within tolerances, add or remove shims to make the required adjustments. The horizontal moves can be displayed in the same way as the vertical moves. Toggle through them and select the one that will be simplest to perform. Use jack screws to position the machine while monitoring the analyzer's live mode until the machine move is complete. If the machine does not move, it may be bolt bound. That is, the bolt is already against the foot and cannot move. Torque all bolts and collect another set of readings to check the work. The job is seldom within tolerances with the first move, but usually requires 2 or more moves to bring it within tolerances. Continue making measurements and moving the machine until it is within tolerances. The laser system setup is very similar to the electromechanical system. Mount the brackets in the same way. The laser heads are different than the electromechanical heads in that they use wireless communication through 3 infrared ports to talk to the analyzer. 2 ports are on the sides and 1 port is on top. Each head has a visible laser beam and target. Before any data can be processed, the machine must be rough aligned so that the beams hit the target during the entire shaft rotation. Adjust the screws until the laser beam strikes at or near the center of the target. Rotate the shaft and check to see that the beam stays on the target during the rotation. If it does not, move the machine until a rough alignment is achieved. After the laser heads have been set up, define the alignment job in the analyzer and enter the data required. The data requested includes the machine type and each component type for the machine, as well as specifying the direction of rotation, the shaft turning speed, the laser orientation, the thermal growth data, and the dimensions of the machine. Steps and calculations are available for identifying soft foot problems. The laser system has 5 methods for measuring that may be selected from. They vary from the totally automatic, where all you do is turn the shaft and the analyzer accepts the readings, to the interactive manual, which lets you be in charge of accepting the readings. The partial sweep is a helpful tool that calculates the machine moves when the shaft rotation is limited. At least a 90-degree sweep is required to make the calculations. The principle used is a patented curve fit, where up to 36 points are measured during the sweep and are plotted to achieve a sine wave curve. Data is extracted from the sine wave to calculate possible machine moves. Another benefit of the partial sweep is it can identify other machine problems such as shaft bind, looseness, and piping strain. After the measurements are collected, display the vertical move solutions. Select one and make the machine moves. When the vertical move is complete, select a horizontal move, then toggle through the possible solutions to the best move. The alignment analyzer can be set in the live mode while adjustments are made. Movements are displayed and updated on the screen to let you see the status of the machine move. The heads compensate for any horizontal shifting from the vertical move and display the updated horizontal solution when the live mode is selected. Torque the bolts to the required amount and take another set of measurements to evaluate the current shaft positions and check against tolerances. Repeat the procedure until you are within the tolerances. The screen shows the tolerances for this machine with the area under the smallest curve being the excellent range. This curve is defined by a CSI tolerance chart. Since every misalignment can be broken into an amount of pure offset and pure angular misalignment, they are listed here in excellent and acceptable ranges for the various machine speeds. The angular misalignment is measured in mils per inch. For every inch of shaft length, that is the maximum allowable angular misalignment. Offset misalignment is measured at the center of the coupling in mils only because it is parallel and will be the same distance off-center its entire length. The plotted tolerance chart indicates that for a machine in this speed range, a pure angle misalignment of 0.45 mils per inch is very acceptable, and that a pure offset misalignment of 2.5 mils is well within the acceptable limits. However, a combination of the two misalignments puts the point of intersection clearly outside of any tolerance limit. For this reason, CSI recommends plotting angular and offset misalignment together when establishing specified tolerances. Use the recommended tolerances of the machinery components being aligned, that is, motor, pump, and so on. If no tolerances are available, use the tolerances provided by CSI. We do not recommend that coupling tolerances be used. For example, one coupling manufacturer accepts 4 degrees of misalignment per inch of shaft length. This seems reasonable. However, 1 degree is equivalent to 17.5 mils per inch. So 4 degrees is equivalent to 70 mils per inch. As stated earlier, the coupling may withstand this amount of misalignment, but the forces are still transferred to the machine, damaging bearings and other machinery components. When the tolerance chart indicates the machine is well within the limits, then store the job in the analyzer. Remove the brackets, install the coupling guard, and follow the safety procedures to button up the machine. Remove your lockout and restart. When the unit returns to a steady state condition, follow up with vibration measurements, temperature measurements at the coupling, and recheck the data used as a basis for calculating the thermal growth. Another follow-up is to recheck the alignment in 6 months, and if it is within tolerances, recheck it once a year. This is made easier with the laser and electromechanical systems because the alignment job can be stored in a computer database where it can be reloaded into the alignment analyzer at a later date. This speeds up the alignment process. Now only the machine distances and any new thermal growth information is required before measurements are taken. Earlier, we posed a question about hiring a contractor and pointed out that tools don't align machines, people do. A good alignment job includes the pre-shutdown checks, including thermal growth, and the pre-alignment checks, including piping strain, soft foot, and bar sag if applicable. If these checks and corrections are made and properly documented, including the final machine positions, then you are beginning a proactive alignment program and not just performing alignments. While many areas have been covered, we've only highlighted the most common alignment practices and characteristics. We realize that unique design and applications necessitate special considerations for correction of misalignment. Thank you for joining the thousands who have recognized CSI training as leading industry with quality information, instruction, and application of PDM and RBM techniques. Whether you use mechanical systems, electromechanical, or laser systems, we are confident that the application of these tips and techniques will help you succeed in your machinery alignment projects. We look forward to assisting you achieve success in your future endeavors.